It's a pleasure to welcome you today to the seventh of the Provost Lecture Series. Originally inaugurated by Professor Scott Gardner. Thank you very much. We continue the tradition. That is of honoring our campus and our faculty. And in particular, today, I have the pleasure of introducing Joshua Kroll, Assistant Professor of Computer Science. I just found out he was an intern here in 2004 and 2005 under Craig Martel. So he actually goes back a little further than his actual employment date of 2019 as an assistant professor of computer science. His interdisciplinary research focuses on risk management around complex, value-laden questions in trustworthy and responsible AI, cybersecurity, and information privacy. His research has received awards from the Future of Privacy Forum and the U.S. Naval Institute. Now, prior to NPS, Joshua was a postdoc at UC Berkeley School of Information, a systems engineer at the Internet Performance and Security Company Cloudflare. We hope you did really well while you were there. And now you work for the government. And held the NSF Graduate Research Fellowship during his PhD in computer science at Princeton University's Center for Information Technology Policy. Received 2015 for his PhD. Bachelor's degree in physics and math from a little college back east in Harvard, been in the press recently in Cambridge, Massachusetts in 2009. And I also want to take this opportunity just to briefly for us all to thank Dexter, because I know things get a little crazy at the end. So I want to thank Dexter Kennedy now, right up front. The reason we're here, the person who puts this together and makes it happen is Dexter Kennedy. So Dexter Kennedy. I think Dexter has been important in all of these and continues to be critical to the success of this faculty engagement. Sir, thank you.
Thank you. Well, thank you, Provost Newman, Dexter, for coming, everyone online. I guess I'll look at this thing, everyone online. I'll get started talking about the value of safety as interpreted from history. History is not a thing that computer scientists talk about very much, so I like to talk about history as much as I can. And even though this is a picture of a train brake cylinder on a wheel axle, I actually want to start with a different technology, planes. We'll get to automobiles later, I guess. The audience may recognize this plane as the Boeing Model 299, the prototype for what became the B-17. It was built in 1935 in response to a tender the Army Air Corps put out in 1934, looking for a new high-speed, long-range, multi-crew, 4 to 6 person crew bomber, and with multiple engines, was the spec given in the tender. Some people may also know that although this plane made many valuable test flights and demonstrated a high degree of performance and quite impressed the Army Air Corps to the point that they wanted to make a very large order, even though it didn't, strictly speaking, meet the performance requirements. One of the reasons was that the first test flight the Army made with this plane ended in disaster. The accident report says that the cause of this accident was that one of the plane's elevators was in the wrong position during the flight, which is a roundabout way of blaming the pilot for not unlocking the elevator prior to takeoff, putting it into a condition where it would not have been noticeable. I see the Navy students in the audience thinking about that and saying that NATOPS would never. That's true. And the reason it's true is because the reason we have aviation checklists is, broadly speaking, because of this accident. In fact, that goes to kind of the central theme of the talk, which is that when we think about safety and safety control activities, we should think of them as being the ground on which we build the ability to have new capabilities. And even though the tender I mentioned, the Army Air Corps, was won by what became the B-25, the order for the B-25 was very small. I think there were only 180 planes compared to several thousand B-17s produced during the war. So that led to a situation where getting the technology that the Army wanted, the Air Corps wanted to achieve the mission required this safety intervention. Also that intervention has been unreasonably effective in other areas. So this is a graph of deaths in airplane crashes over time in black, and then the blue line is the number of commercial billions of passenger seat kilometers flown during that time. You can see that grows quite enormously up until it comes to a crashing halt during the pandemic lockdowns in 2020. But even during that time, the number of deaths, and it turns out if you graph the number of just accidents and incidents over that same period, is also decreasing in absolute terms. And if you sort of normalize it by the rate of how many planes are flying, how many people are flying, it goes down even more dramatically than is visible in this graph. So if we turn from aviation to another application domain, these are two bridges you may be familiar with from opposite ends of the United States. This is obviously the Golden Gate Bridge in San Francisco and the Verrazano Narrows Bridge in New York. And mention these two bridges for the reason that they're actually almost exactly the same length. They're both just around 1,200 meters long. Even though they were opened at very different times, when each was opened, it was for over a decade, and in the case of the Golden Gate Bridge, for about 3.5 decades, the longest suspension bridge in the world. Now, dwarfed by bridges that have almost double the span, and there will be, I think, even 3,000-meter suspension bridges in the foreseeable future. I mention the bridges because I think an interesting thing about structural engineering to me, whether it's bridges or buildings or tunnels, is that we have come to trust these technologies so much, even though they're really quite advanced technologies, that we don't even think about having to trust them, right? People are concerned about flying in a way that you're just not driving over a bridge or driving through a tunnel or walking into a building you've never been in before. Part of that has to do with safety margins that are used in construction versus in other fields. Part of that has to do with the level of understanding we have of how to build and control these structures. Although that knowledge is hard won. So this is another photo of a different bridge. Some people may recognize it as the Tacoma Narrows Bridge, which is a two-bridge system. The bridge on the right is opened in 1950. And the bridge on the left opened in 2007 to deal with increased traffic on this highway. The 1950 bridge, some people may know, was built to replace an earlier 1940 bridge that failed. And that failure taught us a lot about structural engineering safety in the sense that previously most engineering load calculation considered mostly static load. But the experience of the Tacoma Narrows Bridge failure taught us that we need to consider dynamic load, and in particular, the accident seems to have a lot to do with dynamic load shedding related to fluid loading from wind on the bridge deck, which was, for various design reasons to do with cost savings, much narrower and thinner than it probably ought to have been. The thing I did not know until I started looking into this for this talk is that someone at the University of Washington had been retained to do a study of the bridge loading and how to fix it because the problems were noticed almost immediately during construction. And that study was released 5 days before the failure. So in lots of accidents, essentially all the accidents I'll talk about, there was some visibility of the risk available to the people involved. So I said I want to talk about safety and the value of safety. I think I always like to start from definitions. So when you look at the safety literature across safety methods, across safety approaches, broadly speaking, safety is framed as something like freedom from harm or danger, whether you're looking in a dictionary or whether you're looking in a textbook about safety engineering. If you're in the Defense Department, you look to MIL Standard 882, which is the system safety assessment standard for DoD systems. Mill Standard Data 2 has a slightly more detailed description, which is that safety is freedom from the conditions that can cause death, injury, occupational illness, damage to or loss of equipment or property, or damage to the environment. So really getting very serious about what specific kinds of losses you're considering in your safety analysis. I'm a computer scientist. We, for whatever reason in my field, don't really talk about safety anymore. We talk instead about trust, which has, I think, to do with a decentering of formal methods as an approach and a recentering of things like cybersecurity or, the current sort of craze for responsible AI. Trust, as it's conceptualized in computing, is a little bit different than we think of, a little bit counterintuitive than we think of trust in the context of, I think I was standing in a better place before, in the context of kind of interpersonal relationships. So we often think of trust as a positive thing, something we want. We would like to have a lot of trust in the world, right? Trust is a good thing. Trust is a nice feeling to have. In computing, we think of a trusted component as a component where if it misbehaves, it can break some sort of safety goal or security goal, something like that. And that leads us to kind of confusing sets of claims where we say we're looking to reduce trust in systems, where we're looking for systems with the minimum amount of trust possible. There's even a whole set of standards around so-called zero trust. People might have heard that term. Or trustless systems. If you live in the world of blockchain systems, you hear a lot about trustless systems. There is always some trusted base out there. I mention this definition because in addition to being the definition in computing, it's also the definition used in political science to think about trust in institutions, slightly different, a little bit more nuanced, actually, outside of computing, like most things. Another concept that I wanted to kind of get on the table before getting into the kind of the core material is safety as compared to risk. Risk is about identifying a list of specific failure modes or ways that things can go wrong, specific problems that can come up, and then treating those problems as things to be managed. And risk is a very useful concept. I don't want to sort of diss the idea of thinking in a risk lens too much, and we'll come back to risk in a few places in the talk. But what really comes out of the risk thinking is the idea, people are probably familiar with ideas of operational risk management, right? Most people have probably seen some kind of risk matrix where you have likelihood and severity of risk on 2 dimensions, and you're graphing something that you're concerned about against those likelihood and severity dimensions to figure out what to do about it, whether to consider it as sort of a low, medium, or high risk, and what to do about it. And when you say what to do about it, you're talking about some sort of risk control, something that you may have a framework to think about. There's an AI risk management framework from NIST. There's a cybersecurity risk management framework from NIST. There's a privacy risk management framework from NIST that tell you for all the categories of risk you can have, what controls might offset those risks and how you would lower either the likelihood of the risk coming true or the severity of the consequences of the risk coming true. And from adopting those controls in either the way the framework says you should adopt them or based on your perception of your risk tolerance under the framework or just under your sort of own framing of how the risk tolerance should be thought of, then you can undertake control activities to limit the risk. One reason that I like to differentiate safety from risk is that I've become interested recently in the idea of so-called system accidents, accidents that occur even in situations where it's hard to blame any specific problem, any specific risk as the cause or the primary cause or the root cause. People often talk about root cause analysis in accident investigation. And it's hard in a lot of the kind of big headline accidents that you might come up with in your head to come up with a sort of a specific root cause. People may recognize this as the Chernobyl reactor after the accident in 1986. I'm curious, has anyone seen the dramatization of the Chernobyl accident and the ensuing investigation? many fewer people than I thought, and more of those people are my students than ought to be. So my wife, I forced her to watch it. So homework for the rest of you. So Chernobyl is interesting, right? Should we blame the operators, as the official accident report does? Should we blame operational pressure on the operators to make certain kinds of decisions relating to how much electricity they had to produce before a quarterly production deadline elapsed, reporting deadline, relating to their decisions to undertake a certain safety test before that same quarterly reporting deadline to shake down the reactor after its construction of a new unit on the plant site? Should we think about fundamental design problems in Soviet nuclear reactors? Should we think about the ways in which those design problems were exacerbated by construction site changes that were made without a full revisiting of the risk? Should we think about the suppression of some of that information by the Soviet nuclear apparatus in the process of operating the nuclear power system in the Soviet Union in a way that might have allowed the operators to know, hey, this issue had come up at other plants before, and there were ways of managing it and not putting the reactor into a situation in which it would fail, or when you got into a dangerous situation, being able to walk back from the cliff edge. Information was not available even to the senior scientist responsible for the reactor. So that's a difficult system accident. Another kind of accident that drives a lot of theory of accidents is the Challenger accident. A lot of similar things going on, right? Understanding of risk at the ground level being mixed up with the fact that the company that built the solid fuel rocket boosters to aid the launch of the shuttle was up for its contract being renewed, and so was really eager to perform on this specific launch, which had a lot of high-profile visibility. The failure of those solid fuel rocket boosters could be attributed to a design flaw, or it could be attributed to the fact that the engineers who built it knew that the launch was happening outside the temperature envelope for which the boosters had been designed, which the engineers disagreed with, but not strenuously enough to convince the mission commander to scrub the launch. Importantly, in some of the theory of how decisions are made around accidents, a famous book by sociologist Diane Vaughan argues that the organization suffered from the so-called normalization of deviance, that because they had launched outside the temperature window low prior to this incident, that people felt like it was an okay thing to do, and that had happened a few times, and so that wasn't a problem. The last accident I want to talk about, again, as a computer scientist, we like accidents that involve software. We don't like accidents that involve software, but we're interested in accidents that involve software. The Ariane heavy lift rocket from the European Space Agency in a mission called V88, which was the maiden flight of the Ariane 5 configuration of the rocket, update of their heavy lift Ariane 4. This was in 1996, I think. No one is shaking their heads like I have gotten that completely wrong. Sometime in the 90s. It exploded after 37 seconds. Why did it explode? Because its self-destruct mechanisms triggered. Why did self-destruct mechanisms triggered? Because it was off its trajectory. Why was it off its trajectory? Because it had turned its guidance engines to their maximum deflection because it thought it was off its trajectory when it was actually on its trajectory. Why did it think that? Well, some software crashed. When it crashed, it returned an error code. The main control loop of the rocket interpreted the error code as literal numerical guidance data. Oops. Should we blame the software crash? Should we blame the fact that when the software developers said, we would like to write a simulator to check if the software works on the new Ariane 5 hardware, which is different than the Ariane 4 hardware, they were told, no, that would cost too much. Should we blame the fact that very little other kinds of testing that would have revealed this were done, and that testing was also kind of shut down at the programmatic level? The accident report does a very unusual thing here and refuses to assign blame to a specific component other than explaining what happened with the software and the engine deflection and the self-destruct mechanism. Refuses to assign blame to a specific development function. The accident investigation committee decides everyone's hands are kind of a little bit dirty here, and this is kind of a mess, and we can't really articulate why. And now within that frame, I'll mention that this picture on the right here of the rocket after it exploded was on the front slide of every grant proposal in formal methods in software for at least a decade after this happened, actually quite a bit more. Because when I saw it as a baby computer scientist, it had already been a decade since this accident happened. That leads me to the idea of safety as a cost, right? We often think of safety activities as slowing us down, costing us money, putting the mission at risk. Again, from the computing perspective, we try not to do that. We try to do what? Move fast, break things. We can break things because our things are not real. They're software. Just start them again. Except sometimes it's hard to turn things off and turn them on again. People may remember a couple of years ago, Facebook was gone for a day because they had some trouble turning their network equipment off and back on again. So move fast and break things is something that our friend Mark Zuckerberg has said. Well, we'll get to how Facebook treats that later. But I want to talk instead about how specifically all of this plays out in other kinds of emerging technologies. I think a lot about safety in AI. What is safety in AI? Well, if you want to know the sort of official definition of AI safety, you go to the International AI Safety Report, a 300-page document written by about 90 blue ribbon authors from all over the world. And you find in the glossary this definition that AI safety is the property of avoiding harmful outputs from an AI system, right? Much more restricted than we might think about, such as providing dangerous information to users, being used for nefarious purposes, or having costly malfunctions in high-stakes settings. Why, again, sort of come back to this sort of definitional word salad? Well, because I think this focus on just the technical behavior of the models themselves or specific components of the system is a little bit limiting. Like when you think back to some of these other accidents and their causes and the sort of full view of what safety is, part of the reason for that is the belief that dominates the field that the real risks that we should care about are risks of existential human extinction from artificial general intelligence. Without passing judgment on whether or not artificial general intelligence might exist at some point in the future, I want to remark that we might do well to think of AI or other kinds of emerging computing technologies as sort of normal technologies that are not meaningfully different than other kinds of things. And so saying that we should take this risk, which we don't really understand how it would happen, but if it did happen, we believe the consequences would be so severe that even though the probability is so small, when you multiply that tiny probability by that super heavy consequence in a kind of crazy Pascal's wager mode, you end up with a number that says that, hey, we should redesign global public policy around this risk. It's a bit like saying, what if the moon got mad at us and fell out of the sky and destroyed the planet? We don't know how it would happen, but not enough people are planning for it. We should definitely fund an institute to prevent this. Actually, speaking of, there is an institute called the Center for AI Safety, and they got, again, led by Yoshua Bengio, who was the lead author of the AI Safety Report that I mentioned in the last slide, got a sign-on from a bunch of scientists around the world and also politicians and business leaders for this very short statement, mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. It's a big normative claim. Big if true. One reason that people get very excited about this AGI risk is the notion of AI developing new capabilities. This is where my worlds collide, right? I leave AI discourse, people are talking about capabilities. When I come into the Defense Department, people are talking about capabilities. I put two definitions here on this slide to compare them. One from the AI safety report, which says that capabilities are the range of tasks or functions that an AI system can perform, so very specific technical behavior. And the definition, a definition that is consistent with JSIDS. JSIDS, the Joint Capability Development Instruction, does not really have a glossary, but it does have a conception of capabilities. And fortunately for me, rather than having to read all of JSIDS to find that and figure it out, someone in DonCIO did that and just posted their answer on the DonCIO website, along with a sort of long and boring, too boring to put on the slide, even graphic of how they think about capability acquisition. The JSIDS definition, or consistent with the way JSIDS thinks about capabilities, is that a capability is the ability to achieve a desired effect under specified standards and conditions through combinations of means and ways to perform a set of tasks, which I'm going to shorthand as the ability to do a task in a use case. And it's that last point, the in a use case part, that is missing from the AI industry, the AI research enterprise as a community. And I want to sort of back up one step and ask sort of why, when we think about safety, if we think about safety in a kind of normal technology frame, right? What would it mean to do safety for the AI that we have? Why is that hard? Why can't we just take the safety methods that work for structural engineering and aviation and medical devices and surgery accidents? Why can't we just grab those and pull them over and use them in this new domain? And I think there are a couple of answers that are fundamental that won't change. They're just kind of hard things about this specific technology. And then there's one in here that will go away. And so the thing that is fundamental, most fundamental, that won't change the most, is that AI is the set of methods we use when we don't know how things should behave. Right? Mostly, computing professionals are writing software programs, specifying behavior for a machine computer. AI is a way of specifying the behavior for the machine only implicitly, right? Give me the function which maximizes some objective. Give me the function that results from taking this database of known facts and mashing it together using this set of known inference rules. Give me the function that results from doing this regression analysis on this data set. Even in that simple regression case, you haven't exactly specified for a particular input what the output should be. You've just specified that some function should exist that meets certain criteria. And when we try to build that function and understand that function, we can sort of variously do well to understand what that function is, what it ought to do, but we don't have a full behavioral specification against which we can check its behavior from a safety evaluation perspective. And all the existing safety engineering techniques sort of start from some kind of behavioral specification. And when we think about another kind of fundamental issue is this one at the bottom, it's about latent fragility, right? So I will often hear from students about things that are much simpler than, advanced AI systems, ChatGPT or what have you. that they don't want to use automation in their jobs as military officers because they're responsible for what their tools do. But they can't necessarily know when they turn it on well enough what's actually going to happen. And so you can't really treat the tool like some sort of subordinate or unit under command where you can send it over the horizon to do something. Instead, it acts in a way which is a little bit unpredictable and maybe even confusing to human operators in some cases. Some of that is fixable with time, right, and careful engineering. Some of that is about training. A lot of it is about diffusion of technology and work practices. We'll talk about that a little bit more later. The last thing I'll mention, though, because it will go away over time, slightly out of order on the slide, apologies for that, is that we need some domain knowledge that links together how these tools fail, what goes wrong, with what use cases they're being used in. And I mention that because if we want to say we can assure something is safe to use, like an autonomous car, right? How much testing do we have to do before we say it's okay to put this autonomous car on the roads? Never mind that we're actually testing on the roads already in some implicit sense. The National Highway Traffic Safety Administration has a framework they've helpfully published about how to think about the development of operational domains for some technology and operational design domains, and how to think about taxonomizing those things. Come back to that idea later as well. I want to compare that framing to this idea about risk management, sort of come back to the risk management. I mentioned there's a NIST AI risk management framework, which describes a bunch of classes of risks that might exist. Here I've taken these classes not from the NIST framework, but just sort of from the general set of risks that get studied in the research literature. So we talk about generalization error, right? The thing works in the lab, or it works on my machine or on my data set, but doesn't work when I sort of turn it loose in reality. And there's a whole body of research and set of researchers work around robustness, actually a fair number of people working on aspects of robustness in the NPS department, people who work on adversarial examples and so forth. There's a lot of work on so-called alignment, which you might think of as specification in kind of a requirements engineering sense. If you're being generous, which I'm trying to be, the alignment people are often sort of the most existential risk positive people out there. And they believe that their alignment stuff is doing safety, but really it's doing some kind of behavioral specification, trying to avoid a risk of misbehavior. We talk about bias and disparate impact being the risk, and bias being the bias mitigation techniques or bias detection techniques being the way that we respond to that risk. And then we talk about not being able to understand what the machines are going to do once we have them, like you generate that function, what is it going to do? Well, if it's a regression model, we kind of sort of know how to think about that, right? There's a class you can go take in OR that will explain that to you. Probably a class in another department that will explain that to you as well. Scott's looking at me and laughing. He's a political scientist, and they do a lot of that. There's a lot of research on explanation methods and how we use explanation methods to think about managing risks of not being able to understand what generated functions do. And you can go on and list the risk. And I put this up here to make the point, not so much that like these are the right things to do or the right risks to consider, but actually we don't know what the right risks to consider are. How do you know you've gotten all the risks you need to get? If I list out any number of risks, if I go to the International AI Safety Report, which has 200 or so pages in it on risks, how do I know that those are the right risks? They're described abstractly in the report, but actually I think the real risks that matter are the risks that affect how things work in a use case, and that's not something that we really have access to. I'll pause here and do a little bit more history just to say that the struggle for trying to bring these safety methods into computing is not new to AI. It's something that computing has dealt with for a long time. I've put up here because a thing that I've started doing is trying to study this problem in cybersecurity, why study it in cybersecurity, the practices are much more established. There's a huge, giant governance structure just in the Navy to do this. And you can see how that plays out across commands, across services, across DoD components, across the government more broadly, and civilian agencies where things work a little bit differently. We've passed 50 years since the first study that tried to identify a list of risks for cybersecurity, way back in the mid-70s. That work led roughly linearly to the development of this standard, which for obvious reasons is known as the Orange Book. It's a list of requirements for cybersecurity issued by the Computer Security Center, operated by the National Security Agency, even in 1979 when the first version of this was issued. This copy is from 1985 because that's the image I can find. But that's not the only software safety standard out there. There are a bunch of software safety standards that exist. We think about how safety engineering works in the software safety frame. One of the kind of big early studies was a study of a failure of a software-controlled hospital radiation machine called the Therac 25. Some people may be aware of that. And that study was done by Nancy Levison. Later in her career, she developed this model, which is called STAMP, the Systems Theoretic Accident Model and Process, to explain how accidents come up and to try to capture those system accidents that I started with and understand how those happen and how they fail. And I like a few things about this model. One is that if you look at it, it starts way up at the top, thinking about legislatures and the law, and it flows down sort of through regulation to behaviors of organizations and companies and their incentives and normative concerns, all the way down to concrete work in development and operations of a real operating process. And it's this thing in the red box in the lower right corner of this figure that as engineers we're mostly trained to think about. But that's not the system. The whole diagram is the system. That doesn't mean we shouldn't spend most of our time down here in the red box. But if we ignore, if we say, oh, all of that other stuff, it's management, it's like, I can wave my hands at it, it's fine, it doesn't actually affect anything, that's a mistake. In my group, we think about, I like to refer to it as socio-technical AI safety or socio-technical safety more generally. So thinking about safety in this frame from kind of the STAMP view that safety includes a variety of concerns, not just technical concerns, but also human factors concerns, organizational factors concerns, translation of policy, fidelity of translation of policy, all these kinds of things play in. And so some stuff that we've done in recent time and are doing actively right now, thinking about emergence of problems. So last year for CDAO, we did some work actually using the STAMP model to study a bunch of different well-studied AI deployment scenarios to see if we could do a better job identifying risks, identifying hazards, not risks, hazards, ways that the system can fail with less effort or faster or more reliably and translatably than prior kind of ad hoc unstructured approaches to studying those same application domains. And that's interesting because it sort of gives you a touch point to say, like, how much does this system safety lens that I've been bantering on about for half an hour now help us over and above, you know, kind of traditional study design techniques? Does it allow us to see further faster? How much is a little bit hard to quantify, but qualitatively, are we finding the same problems? Are we finding them with more effort, less effort? Are we finding them faster or not? So that's work that has led to a bunch of theses and one PhD dissertation. One particularly interesting piece of that work, and I'll come back to the idea of ethics and human values in a few minutes, but was a thesis that was joint with a student in the Defense Analysis Department looking at how we could think about requirements for responsible use and operationalizing ethics in the military use of an uncrewed surface vessel. That work does a nice job at the end, sort of mapping across from kind of technical control requirements to the specific details of doctrinal responsible use for military purpose. So I quite like that. Out of that work and also the other stamp work that we did, kind of comes the importance of thinking about human-machine teams and how to assess human-machine teams, and thinking about what are the human factors, assessment requirements or design requirements that should support good systems. One thing I think is interesting is human factors often tends to think about the psychology of individual operators or decision makers. And so you see a lot of studies in this space, like, did the image processing system get the same answer as the radiologist? And did telling the radiologist about any differences change their decision, and under what circumstances? And that leads you to just this confusing morass of studies. There are a zillion of these studies, and they all say different things, and it's very hard to turn that into actionable knowledge. The thing that I think is interesting, that sort of relates to some of the discussion of system accidents, is thinking about how that plays out in terms of organizational factors. And so here, one of my students is here today, Captain Burke, who's studying how score-based decision aids used in the Marine Corps should affect or might affect promotion decisions by a promotion board. So suddenly everyone in uniform is awake. Those models are being used today already by the Marine Corps, but as far as we can tell, they aren't getting a whole lot of careful assessment yet, other than sort of baseline performance assessment on some data that the Marine Corps Manpower and Reserve Affairs, what do you call part of GCOC? Deputy Commandant, I guess, office has been thinking about. And I have another student here, Captain Blank, who is looking at ways that models might affect things like financial planning. So that's kind of another place where you can lift some of these concerns up to the organizational level and not think about so much individual decision making. Mentioned I'd talk about use cases again. So a thing that people are really very, very curious about, partly because the companies that operate big so-called foundation models like ChatGPT or Google's Gemini are very close hold, even internally, even to their own researchers, about what people use these tools for. The CDAO ran a survey across DoD looking for use cases and collected 250 or so use case narratives from across DoD. So working to analyze those to try to build this taxonomy of operational domains, design domains for these systems to provide that grounding point for assessment. And thinking about how you can build from that towards assurance, towards meaningful cases that the system will do the right thing under a certain situation. Another bigger project that I'm really hoping I convince my co-authors that we can put this online is thinking about how to learn from accidents, right? So I didn't look up all of those accidents for this talk. I had been spending a couple of years thinking about those accidents and all of the features and facets and what we can learn by looking, because once you start looking at system accidents, they all kind of look the same. I don't know if anyone here went to it, but there was a talk a couple of years ago now from someone from the Norwegian Navy. Raise your hand if you when you recognize that you've gone to this. That was here about an accident they had where they sank one of their frigates in home waters. And the talk was billed, if you pull up the email for it, as the time we sank one of our own frigates and nothing broke and nobody did anything wrong. And it's a system accident. The whole talk was about everything that broke, all the things people did wrong. And each time one of those things was identified, the guy was the head of the accident investigation report for the time leading up to the collision that sank the collided with an oil tanker. He would say, well, you know, we operate under that condition all the time. Condition by itself, not fatal. The sum total of the conditions, the system, the interactions, sank boat. It's kind of a fun accident to look up. The Helge Ingstad is the name of the frigate. Fun because lots of kind of dramatic pictures of it on its side after it sank in very shallow water. But the point of all of that windup is to say that if you start looking across system accidents, you learn things about what the conditions are that lead to failure. And I think the biggest learning, I don't want to get into all of these, the biggest learning is that failures come from the structure of the systems. And we try to foresee that structure. If we could foresee that structure, we would design the system so it didn't fail. The fact of a failure tells us that we didn't do that design properly. Accidents are revealing that structure to us. And if we can keep track of that information, we gain the epistemic knowledge that we need to do safety analysis later. I think I've harped on enough, but I'll just say it again, that making components reliable does not make systems reliable. So I would come back to ethics. Ethics is difficult because when we talk about ethical principles, they're abstract. They don't formalize well into rules that we can put into machines. We cannot make machines ethical. That is a category mistake in at least two different ways. But what I do think is interesting is we can treat safety analysis, as I've described it in this kind of full system socio-technical framing, as a way of enabling not just adoption, but responsible use, for the same reason that I said that people will turn things off if they don't buy into it. Something that I like to use as an example here is we talk a lot about how to build ethical AI or build AI in a way that it can be used ethically. We do not talk about building an ethical service issue rifle. Why not? We understand that the control on whether people are using service issue rifles ethically, or at least within the doctrine, right, happens elsewhere in the system. The design of the rifle supports it. Having rifles that don't explode when you fire them supports that goal. Still important to have a test plan for your service rifles when you buy them. Still important to have a training program. People know how to use them. Important people know how to clear a hang fire, for example. Not part of the design of the rifle. A friend who's a real moral philosopher, a fake moral philosopher, I'm afraid, who defines ethics as the organizational capacity to reason about operationalizing values. And so we can state our values, right? DoD has 5 AI principles, like companies, because the Defense Innovation Board told them they should. DoD also has core values. The Navy has core values: honor, courage, commitment. People know. What does it mean to take those core values and put them into a machine, or even set them in a use case to say that when we use the machine to do a task capability, that we are upholding those values, or that we can continuously ascribe to what we're doing conformance to those values. That's challenging, but I think under the safety framing, at least tractable. Can't end without explaining the name of the talk. Very briefly, right, when trains were an emerging technology, so let's go back 130 to 150 years, the way that trains slowed down and stopped is that there were handbrakes on every car, and there were people who turned those handbrakes under an order from the train captain, engineer, or the conductor. After receiving a signal, the brakeman would run from car to car on a walkway over the top of the trains and turn on the handbrakes. It's a very dangerous job. Got crushed between the cars a lot, fell off a lot, hit by oncoming tree branches, low-hanging masonry, that kind of thing. Tops of tunnels. Also, you see something you need to stop for. Something's on the tracks, another train, animal, avalanche. Got to do this in bad weather too. Send the stop signal. Crew has to run from car to car, setting all the handbrakes before the train starts slowing down. Your stopping distances are very long. Solve this problem came the idea of so-called, I skipped it, so-called continuous braking, right? That you could have one brake application control operation, which would apply the brakes across the entire train. Patented in 1871, earlier slightly in Germany, a variant version of it, and also in the UK, but the really popular one that took over the industry around the world, not just in the US, but specifically in the US, was designed by a man named George Westinghouse, the Westinghouse air brake. And the Westinghouse air brake was patented in 1871, started kind of being installed in trains in 1872, allows the engineer to push a valve, releasing pressure from a pipe, triggering a valve on each train car, which would then set the brakes. And the design of the system had the property that if the system developed a leak, if the train was broken in two for any reason, came uncoupled or something, that the brakes would set on the cars that were disconnected from the engine. And that is a fail-safe design, as opposed to competing, say, vacuum brake systems, which fail open rather than closed. The Westinghouse air brake takes over the industry. But how does it take over the industry? So this is the part that I jumped ahead on. It takes over the industry by taking over the passenger rail industry. Why does it take over the passenger rail industry? Passengers care about the trains not getting into accidents. More people will ride the trains if the trains aren't likely to crash. It's the 1870s, trains are crashing all the time. It does not take over freight rail, at least not for about 30 years. Why? A couple of reasons. One is the gains from the brake are not felt as much in freight rail because freight train sets are in general longer. And the design of the particular first versions of the brakes have the property that the brakes on the end of the train could be applied maybe tens of seconds later than the brakes near the engine, where the conductor is, or the engineer is activating the control lever. And so if you stop suddenly, as is done in some braking trials to try to demonstrate the value of the brakes to sell them to the freight industry, the back of the train kind of collides with the front of the train, creates a shock that can damage the cargo. But they do get adopted partly as well in the freight industry because rail freight would like to take advantage of the big gain from the train brakes, which is that by lowering the stopping distance, you increase the speed at which you can operate safely and still stop before you hit the thing that you want to see. Also advances in the train order system at this time, which is really interesting. Total parallels to everything going on in emerging technology today. Just amazing stuff. Ultimate end of the story is that that Congress passes this thing called the Safe Appliance Act in 1893, and that leads to a requirement to put these brakes on. The other big kind of barrier to adoption is passenger train sets are generally operated by one company, and so you can buy one technology, hook them all up together, and it works. Freight at this time is moving around, sort of, there's starting to be a national rail system. Cars are moving between lines. They're moving on tracks that aren't controlled by the company that owns the cars. And so buying new technology and having someone else operate it or getting it into a yard where it's not interoperable with the other things in that yard is a problem. So I'll conclude by saying that we need to have safety. Like the lesson of the train example is that we need to have safety to get the benefits of new technology, right? So to move the same train equipment from running at 40 miles an hour to running at 60 miles an hour, it's a big difference. We needed to adopt the technology. To get access to emerging technology, new capabilities from AI, we need people to believe in those capabilities. We need to think about how to get that belief in a socio-technical way. We need to not just design the technology that makes things safe, develop the assessment techniques that allow us to do the assessment, but think about things like training and reshaping of work practices. Had another student who graduated recently who was studying work practices around Navy communications system, which was deployed in 2005 and still is unused. Because diffusion is hard and changing organizational work practices is hard. And also it's not the program office's job to change the organizational work practices, but it is their job to buy the system and install on the ship. I mentioned that I like to compare this in cybersecurity. A comparison I think is interesting that's positive is like big websites, Google, Facebook, right? They're always there when you go visit them. If you go home and you visit google.com and it doesn't work, you don't think maybe Google is down today. You think maybe my Wi-Fi is down. There's a reason for that, not just because it's incentive compatible for Google to be up all the time because they get their money from you visiting their site and using their product, but because there's a whole set of technical and organizational structures that support high reliability function in that space. And so that's where I'll kind of end off and take questions, which is to say that move fast and break things did actually, this is true, it's not a joke. Looks like I photoshopped this, but I promise you that I didn't. It's just a terrible photo. Mark Zuckerberg eventually decided that the koan of Facebook was not move fast and break things, but move fast with stable infrastructure, except somehow their graphics people could not fit the whole word infrastructure on his slides. So move fast with stable infrastructure. Thank you.
We have a few minutes for questions, so please.
Take some questions in the room, but I see there are questions online too. Questions in the room first. You came, so you get priority.
Questions in the room? Well, please. Katie.
Dr. Kroll, thank you so much for your talk this afternoon. It was really insightful. Would love to hear your thoughts around how do we ethically develop AI capabilities and other capabilities that can counter capabilities being developed by an adversary that may not taking ethics into consideration, especially in regards to AI.
So yeah, so that's actually kind of the motivation for this framing in my head is the cognitive dissonance that I experienced teaching in, and Professor Kolsch isn't here, I don't think. Maybe he's online. But he teaches an executive education course for leaders on AI. And I gave a responsible AI talk at that. And now CAO has their own responsible AI content that has been approved by the Public Pre-Publication Review Office in OSD. And so they use that content now. I don't give that talk anymore. But that talk always led to a discussion with the flag officers in the room. That's sort of exactly your question. And then I would go teach my responsible AI seminar at NPS, and students would tell me about their experience. You know, this is the partially automated surveillance or weapon system that was put into our unit, and we turn it off because we don't believe in we're responsible for its behavior. And so like that's a setup for now. Like the real answer is right, we have to think about training as well as like I meant to mention the .NLPF, right? But when we think about capability assessment, we're thinking about not just technical function of the artifacts, but we're thinking about how does that technical function shape and kind of co-develop the doctrine needed to use that thing? How does you know, all the other elements of the .NLPF play out there? So I think that's one thing. And also, right, the point of the service rifle story is to draw a contrast, but also to say, like, we have the tools to do this, right? We can do this. We're broadly pretty good at this. There are some things that are fundamentally hard about the new technologies, but I don't think they break the systems that we have in a way that we can't adapt to them. I think the other thing to mention is that our adversaries do get this, right? If you look at, let's say, Chinese technology policy, there is an enormous amount of focus on assurance and control and ways of figuring out how to deal in practical ways with safety. and with cybersecurity and with power of corporate actors. And so that's something that people are thinking about. Now that's not to say there aren't, other, like, an interesting problem, I think, is that we live in a world where the technical capability gap between sort of what an undergraduate student in computer science can build and what is a dangerous weapon that is definitely out of control is not that big. And what does that mean for, rogue groups, TCOs, that kind of thing? And that's something that we don't talk about enough, I think. But that's important.
Thank you.
There's a lot.
Yes, we have time for a question online.
Yes, there's one question online from Aaron Julo. He asks, what if we use AI to help us generate use cases and then evaluate the risks inherent to these use cases? Therefore, AI as a tool to provide us with a starting point for defining potential risks in these use cases.
Yeah, so that's an interesting question. Question is, sorry, I'll repeat it because I'm closer to the mic than Michael is. The question is about, can we use AI to generate the use cases we need to figure out the taxonomy of use cases to do analysis? And I think the answer is it might be helpful to suggest use cases in this way, but the tools that we have will repeat what they are trained to do. Like, they rely very heavily on data that's scraped from the internet. And so the use cases that are imagined for them will be limited to things that people have talked about already. And also will come in a kind of unstructured way. And if we can kind of gather that information in a more structured way with a survey that we kind of understand how we've administered it, then we may be in a better position, is one part of the answer. I think the other thing is trying to look too far down the road is a little bit futile, right? If you put yourself back at the beginning of the steam engine, right, you probably wouldn't predict all of the consequences of industrialization. They're complete reshapings of systems. I mean, when the Navy thought up containerized shipping in the 70s to deal with the logistics problem during the Vietnam War, I don't think they thought they were also hollowing out inner city Baltimore.
Oh, thank you very much. Let us thank Professor Kroll once again, and we'll